Hi, everybody. It's Dr. Chabot. Today, we are going to be talking about 2D and 3D integrals for calculating moment of inertia or center of mass. So if we look at these equations, right, we have the equation for moment of inertia is the integral of r squared dm. And then we have the integral for the center of mass can be written, and I'll write it in the x and y equations. For the x position of the center of mass, I have the integral of x dm over the total mass, which is just the integral of dm. And then I have the y location of the center of mass, the integral of y dm over the integral of dm. So if we look at these integrals, when we are doing a single dimension, right, in 1D, we've seen that we can write that dm, which is just, again, a tiny bit of mass, can be written in terms of a length by using a density function, a linear mass density lambda, times some length of your tiny mass dm, right? This is the length of your tiny mass, right? If we just have a little bit of mass dm, then dr is that length. And lambda would be our linear mass density. So that would be our mass divided by our length if it was constant, or it would simply just be a function of the density as a function of length only. So in 1D, that works out really nicely because everything in 1D can use the same dr because it's just a tiny little bit of length. In 2D, the problem, and 3D, the problem becomes with these integrals very often is figuring out what to use for dm. And a lot of times that's going to be informed by the symmetry. Once you decide what to use by dm, then correctly drawing your r squared or your x or your y in these integrals will then allow you to solve that correctly. So we want to focus first on the idea that all of these integrals involve dm, but they also are actually integrals over spatial things like r, x, or y. Okay, so let's go ahead and focus on dm. And let's do that in 2D and 3D. So the best way to do this is kind of just to see a couple examples. So one example would be the moment of inertia of, and let's just say here that it's going to be some solid disk. So I'll say a solid flat disk. And let's give that disk, let's say it's uniform. If it's not uniform, you'll see how you can change that out for a function. I'll point that out here. But let's say that it's a uniform density. Just for this example, let's say it has a total mass m and a radius r. So I would have here some radius of the entire circle, r, and some total mass m. Great. So in terms of what dA or dm could be, in 2 dimensions, dm can be written via the density by an areal density, mass per area, times a tiny little bit area. Just like in 1D, it was the mass per length times a tiny little bit of length. Here, we have here a mass per area times a tiny area of our dm. So I can write out sigma because I just told you it was a flat disk. I know the area of that disk in terms of r, right? It would be pi r squared. I know the mass, I'm given the mass m, or the problem could give me some variable density. So I could figure out sigma. The question then is, what do I use for dA? And that relates to what I choose for my dm. So in this case here, because it's the circular symmetry, I can choose a dm where I use a nice kind of ring, a little thin ring of some very infinitesimally thin little hoop, basically. And let's check to make sure this works. So I need to use this for moment of inertia. In my moment of inertia integral, if I look at that, I have the integral of r squared dm. The main requirement is that all of my dm, all parts of my dm, have the same r squared, because I'm going to be adding up all the little r squared dm's. So for this particular thing, remember r is going to be the distance from my pivot to my dm. And I hadn't specified earlier, I should have said that this was going to be pivoted at the center. So pivoted through the center. Through the center of mass for an axis that's perpendicular to the page. So that in this case, right, the r here would be, in fact, going to be the distance from my pivot to any part of my dm, and they all that little ring has the same r squared. So I'm allowed to use that in this particular case for this integral for my dm. Awesome. So now I've identified a dm to use. And if I've identified my dm, sorry, I lost my note. If I've identified a dm, then what I can do is try to figure out what my dA is for that. So if this is my dm, now I need my dA for this dm. So the dA is just the area of that thing I drew. And we do approximate this in the same way that when you do like a Riemann sum and you imagine it being the sum of all the little areas underneath a curve, those are all little tiny rectangles, even though there's a curve, right? Because as you make the width of those rectangles get infinitesimally small, then that approximation doesn't matter. So it's the same thing here. So what we want to do is we want to basically imagine unfolding this. So imagine unfolding it or unwrapping it, however you want to say it. If I have a circle, right, you're going to like undo it and lay it flat, right? So if it was a circle like that, I'm laying it flat. So if I'm going to be unfolding this dm so that it goes from a circle to a line. So again, I've taken my circle and I've just made it go straight into a line. So the whole circumference of it up here is still this whole length. And that length is our circumference, which we can see was at a distance r. So that length is 2 pi r. And that is my little r because it is the variable distance from the pivot to dm. So that's not my capital R, it's the radius of the little bit of dm that I drew. And then remember that this is an infinitesimally thin ring. So this distance, the thickness here, is going to be very small, and that's what we call then dr. And so I have this tiny little ring, very, very thin. It has, if I imagine unwrapping it, it has a height dr, and then a length 2 pi r. And so what I can see just from knowing how to find the area of a rectangle, that dA, which is the tiny area, is just going to be equal to 2 pi r dr. Once I know dA, then I'm really pretty much done because like I said, the rest is just figuring out what the areal density is and then figuring out what to integrate from. So I'll show you for this particular one how to do that so that we can see it the entire way through. Once I have dA, I can then see that I want to go back to put this into dm. So my dm is equal to my sigma dA. So that would be equal to sigma 2 pi r dr. And again, at this point, I might in my problem be given some sigma that varies with, say, radius. Maybe it gets less dense as the radius increases, right? So I would be able to plug that function in here and then have something to integrate. Or if it's uniform density, like it is in my case, then my sigma is just going to be equal to my total mass, m, over my total area, right? Which is then pi r squared. Pi r squared is my total area of the disk. And so this is going to be equal to a constant. Okay, so let's go ahead and put this all together. So I have my moment of inertia integral is the integral of r squared dm. Now I have dm in terms of something in terms of r. So this is great because I can actually do this integral. So it'll be the integral of r squared, that r is a variable r, the distance to my dm. And then I want to plug in for my dm, which is going to be equal to sigma dA. So I'd say sigma dA. And so I can say sigma 2 pi r dr. And again, if it was a variable sigma, I would just plug that in here. It is a uniform sigma, which is a constant. So I can actually pull that out of the integral in the next step. But at this point, my integral is missing limits. And so that's when I look at my dr and I say, okay, let's go back to the diagram and try to figure out what my r will vary from. So if I look at this diagram, I can see that I'm going to add up all the way from the center of the circle, where r is going to be equal to 0, all the way to the dm's out to when r is equal to the end of the object, capital R. And so I want to go from 0 to capital R to add up all of the r squared dm's for my whole object. So the limits then become 0 to r squared sigma 2 pi r dr. And again, that looks a little crazy maybe at first, but again, methodically adding it all together, it should make a lot of sense that what we're doing is we're really just writing out our dm via a density function in terms of our spatial parameters of the object, right? So writing out the density and then writing out the area of that dm. So if I execute this integral now, I can then find my moment of inertia around the center axis for this flat disk. So I can pull out my constants. So I had my sigma, which is a constant, m over pi r squared, and I'll pull out that 2 pi as well from that 2 pi r. And then I have 0 to r of r cubed dr, which is just m 2m over capital R squared times r to the 4th over 4. And that came from me just saying that this was equal to little r to the 4th over 4 evaluated from 0 to capital R. So to fill in that step there, and then you can see that my r's will cancel, my 2 and my 4 cancel, so I end up with 1/2 mr squared, which is the correct answer. Okay, so we can see that some of the challenge is just figuring out what dm is and then writing out a dA for that dm. So let's look at a couple other examples. Since we're in moment of inertia mode, let's go ahead and write out or look at a moment of inertia of a solid cylinder here. So I have all of these notes already posted alongside this video, these PDFs of these notes, but I just want to talk through it in case that's useful to anybody. So here I have a solid cylinder. It's going to be the same as a flat disk. We already know the result from our moment of inertia table is going to be 1/2 mr squared, but let's show it. And now we have a 3D object. So we want to pick a dm based on symmetry. And instead of talking about a tiny area, like in 2D, or a tiny length, like in 1D, for 3D, we're going to have to talk about a tiny volume of our dm. And so here, the dm is just going to be a cylindrical shell. So some cylindrical shell that is infinitesimally thin, kind of like our ring, but extended upwards. So here I just have a paper towel that, right, we can imagine that's like then our dm, and that has some variable distance r that points from the center axis to the dm. And if I want to find the volume of this, I would first want to know my surface area. And then I would want to know the thickness. And if I knew my area and my thickness, I could get that volume. So that's basically what we want to do here. Is you can see that in these notes here, I've basically talked about unfolding that DM. So basically unwrapping it, right? Taking it from, like I did with the paper towel, taking it from this cylinder like that, and then instead laying it flat. And then it has some tiny thickness, right? The thickness of the paper towel, which we're calling DR, and some area, which is then the surface area of that flat part of the cylinder. So 2 pi r, the circumference, times L, which is in this case the height of that cylinder. So that gives us our volume for that DM. And if we have our volume and we have our density, then we can get our DM from that. So that's an example of what this would look like in the solid cylinder and for moment of inertia. And again, what's important is that every part of this DM is the same little distance r from that center axis, or else it won't work because I can't then add up all my r squared DMs. Let's look and see what it looks like for our center of mass integrals. So for center of mass integrals, remember that a big difference is that these variables in the center of mass, the y, for example, in the integral y dm, that's now the actual position y relative to the origin. And so what we did in class, this is the one that we worked through in class, we have the polar coordinates for this semicircle. And we took a tiny little bit of DM and we used what we know about polar coordinates to find the tiny little area of that tiny little DM. And so this walks us through all those steps. But again, it's all about finding your DM, finding your area of your DM, and then using the density function to relate those. Okay, and then the most complicated mathematically example is going to be to look at this triangle here. And this is going to be, let's say we want to find the center of mass of this triangle. And it's again solid and uniform. Then we can see from symmetry that there's not going to be a center of mass in the vertical direction that's not just along y equals 0, right? So y center of mass is very simply going to be equal to 0. And so that's what we have written over here, is that the y center of mass is equal to 0 right there. The x center of mass, though, we do need to find, and it would be somewhere along that x-axis. And so we can choose a DM then that matches that symmetry that we're just looking along that one axis. We need them all parts of our DM to be the same distance x from the origin. So you can see that in this one here that I've used, that every part of my DM is that same distance x over from the origin. And so that then allows me, so the horizontal distance, right, from it. And so that allows me to then use this as my DM piece for the center of mass calculation. So then I draw my DM, and this is where we make the approximation that it's a tiny little rectangle, even though it might be a little tilted at the top and bottom. Again, as we get infinitesimally small, then that doesn't matter, and we just treat it like a rectangle. The thickness would be some tiny dx. The height is 2y dy. And now we've done really, the basics of trying to write that dA in terms of our spatial variables. So we end up with dA is equal to 2y dx. That's our area of our DM. Yes, that's strange, right? Because how are we going to do that? But we'll worry about that in a second. So let's go ahead and see where we're at, right? So we can see that we have our sigma, our mass over our area, same old, same old. So we can write our DM here as shown, that DM would then be equal to our mass over our area times 2y dy. Great. But as you may have noticed, and what's outlined here, the issue is that we have this 2y dx, and that's strange. So we need to get y in terms of x, which we can do because we took algebra. And so we remember how to write equations for lines. I walk through that process here. You're really just writing that equation of a line using y equals mx plus b. Once you've done that, you literally have y in terms of x. You can plug that in for y, and then you have an integral you can do. So that has nothing to do with the physics that we're learning. That's like a math trick that either you've seen before in your calculus courses, or you will see at some point soon. So you go through, you put it all together, and you end up with some value for the center of mass. And again, I think that the most confusing things often are figuring out what your DM is, and then figuring out what that area of that DM is, and then doing any little math trick you need to do in order to actually solve that integral you come up with. Okay, I hope this helps. Let me know if you have any questions.